So we have said H and S are relatively temperature independent. Yep. But we've said G is very temperature dependent. So as temperature changes, G changes significantly. Let's investigate our interesting scenarios. What I mean by interesting scenarios, as we've seen a couple of times color-coded, there are 4 possible combinations of H and S to give us a G, H minus T delta S. You can have a plus plus, a minus minus, a minus plus, and a plus minus, right? The temperature-dependent G values were when the signs were the same. So one example is when H and S are both positive. H positive, not generally favorable, that's why it's red. S positive generally is favorable, that's why it's green. Okay, so if we are plotting G at low temperature, our reactants have lower free energy, lower Gibbs free energy than our products. So it's a positive value to go from reactants to products at low temperature. It's spontaneous to go from products to reactants, aka it's spontaneous in the reverse direction. That's what we have said sometimes. Non-spontaneous to go forward, but spontaneous to go backwards. As you increase temperature, your value of R and P, your Gibbs free energy associated with R and P, changes to be at these new levels. The R becomes lower, the P becomes lower. They get closer together, but it's still non-spontaneous. As you continue to increase temperature, you get to a point where the reactants and products have equal free energy. And so delta G of this kind of state at this temperature is equal to 0. Products and reactants have the same G value, so products minus reactants would give us 0. This could be the melting point, the boiling point, the freezing point, that sort of thing. This could be a phase transition temperature, changing state from solid to liquid, liquid to gas, gas to solid, etc. Because at this point, at those points, melting points, boiling points, G is equal to 0. And we've actually seen that if we set our G equal to 0, we can solve this equation for T and get T equals H over S, T equals delta H over delta S. We could solve for the temperature at which, whatever this reaction is, happens. This melting point or boiling point. I say melting point, boiling point, and I should specify, because it's endothermic, it has to be going from solid to liquid or liquid to gas. You have to be putting in heat energy for it to happen. So it cannot be a freezing point because freezing points are exothermic things. So yeah. It has to be melting or boiling because it's endothermic. Okay, so if I continue to increase temperature, up here, remember we are subtracting this T delta S term. And so as I increase temperature, this T delta S term grows larger and larger and larger. And because we are subtracting, eventually delta G becomes negative. Eventually, reactants are on a higher shelf than products, and delta G, delta G becomes negative. It is spontaneous once our temperature gets to a high enough level. We say this reaction is entropy driven because, again, it's when this term gets large enough that G becomes negative. And so raising the temperature causes this term to get bigger and bigger and bigger, causing this reaction to be spontaneous once you reach a high enough temperature. Okay, this is for an endothermic reaction with a positive delta S. Continuing to talk about an endothermic reaction with a positive delta S, if I make a plot of temperature versus energy, H as a function of temperature, this is not H multiplied by temperature, but H as a function of temperature, we've said H is relatively temperature independent. So I'm going to flatline my delta H for a given reaction. If I plot T times delta S as a term, as temperature increases, that term grows larger, so I'm putting it with a positive slope because T delta S grows larger as we multiply by higher and higher temperatures. At this point where that intersection happens, that is where delta G equals 0. And if we look, prior to that term, this delta H value, is a higher number than this T delta S value. But once we cross over that threshold, this part is the dominant term up here. So prior to the boiling point, melting point, whatever this transition temperature is, prior to that, the delta H term is dominant, and our G stays positive. After that point, this term becomes dominant, and I'm subtracting, so that's what allows G to become negative. It's positive over here, it's negative over there, it's 0 at the intersection of those two lines. It's spontaneous when enthalpy, dang it. It's spontaneous when entropy, when the entropy term in our equation starts to be dominant. Got it? What about an enthalpy-driven reaction? Enthalpy-driven, that's the delta H is negative, delta S is negative. It's when this term is dominant that this delta G is negative. An enthalpy-driven reaction is spontaneous at low temperatures. So at low temperature, reactants are higher than products. It is spontaneous in the forward direction at low temperature. But as you increase temperature, this term becomes bigger, which makes your G less negative. So our shelves change accordingly, and we click, click, click to where you've reached a temperature that it is no longer spontaneous because this term has become too big that it's forcing G to be positive. So enthalpy-driven reactions, spontaneous at a low temperature when this term is small. Entropy-driven, spontaneous at high temperatures because this term gets big. G is 0 at this point where reactants and products have the same delta G. For entropy, enthalpy-driven, it doesn't matter. And we can find, in this case, a freezing point, because freezing is exothermic, or that's liquid going to solid, or a condensation temperature where gas becomes liquid, because those are exothermic processes. Yep. Yeah, I think I've said it all. We'll look at another one of these plots. We've got a negative and a negative. Delta H, it's flatline. Actually, I drew like it's at 0, but that was silly of me. It's flatline at some negative value. If you look back at where our 0 was last time, delta H was a positive value, so it was above 0, but now delta H is negative value, it's below 0. T times delta S, this is a negative sloped line this time because this S value is a negative value. Same as before, that intersection of those two lines is where delta G equals 0. On the left of this graph, we're looking at most negative delta G, so that delta H term is lowest. And when that H term is lowest, like lower on the graph, lower than that line, when that H term is lowest, that's spontaneous because that term is dominant. And then past that point, T delta S starts to take over, causing your G to become positive. Prior to the temperature where G is 0, it's spontaneous. After the temperature where G is 0, it's non-spontaneous. Okay. Got it? Got it. We got more to say. G versus G. What the heck? G standard versus G non-standard. We've been calculating a lot of G standards, even though we haven't exactly specified the difference between the two. We've been calculating a lot of G standards, and we've not really calculated non-standards, but it's time to define what non-standard G really means. Elements in their standard state are defined as having a Gibbs free energy of 0. Their standard state means 1 atmosphere for gases or 1 molar concentrations for liquids. So standard has these specifications that we haven't previously defined, 1 atmosphere or 1 molar concentrations. So if I measure the free energy loss when some elements combine to form some sort of reactant at 1 molar solution, I get a little shelf down here. But if I have a solution that's not 1 molar, it's more dilute than 1 molar, I'm going to release more energy in this. The Gibbs free energy is more negative for this quantity than it is for that quantity. The reason being, hold on, it's going to come up here. I'm going to say that. The reason being, come on, you have an increase in entropy as you go from a 1 molar to a 0.05 molar solution. And that increase in entropy causes your G value for this solution to be different from your G value for this standard solution. Okay, numerically, what does that mean? This is something you can find in the back of a table. It's delta G standard at 25 Celsius in the back of a book. This is what we will call the correction factor for non-standard conditions. So for this specific example, I put in 0.05 molar on top of my equation there. 0.05 molar divided by 1 molar because that's non-standard over standard stuff. And I can multiply by RT, where R is 8.314 joules per mole Kelvin and T is 298 Kelvin, or doesn't have to be. But add this little correction factor in, and I get the value where this shelf is actually located for something that's not 1 molar, or a gas that's not 1 atmosphere. The actual correction factor for this thing, when I plug in a 0.05, is negative 7.42 kilojoules per mole. Why did I say it that way? I don't know. Negative 7,420 joules per mole. That's a significant change to go from 1 molar to 0.05 molar. That can make a big difference in your reaction overall and whether it's spontaneous overall or not. Okay, this is how you determine delta G for a single reactant that was non-standard concentrations. What about when you have a whole reaction that's non-standard concentrations? Ooh, let's write it. So if I know that I have some reactants going to products, the typical way to calculate delta G for this reaction is delta G of the reaction, delta G standard of the reaction is the sum of delta G of the products minus the sum of delta G standards of the reactants. Well, delta G non-standard for the reaction, you have to do delta G non-standard of the products. I don't want to write it. Sure. I'll write it more step by step. Hold on. Delta G non-standard of the products minus delta G non-standard of the reactants. And if I take my little formula from the last slide and I plug in here that delta G non-standard for the products is delta G standard for the products plus my correction factor, RT ln of products. It's products over 1 molar, but products over 1 molar, well, that's going to be products, right? Minus, if I make the same substitution, except this time I'm going to say delta G standard of reactants plus my little correction factor, Ln of reactants. Run out of space, but that says reactants. I can gather some like terms here, and I can say delta G reaction is equal to delta G standard products minus delta G standard reactants, right? I just gathered those two terms together, plus RT ln of products minus RT ln of reactants. Bear with me, I know. Okay, now what? Well, this products minus reactants, when it's both standard, that's delta G standard of the whole reaction, right? Delta G of the reaction, non-standard, is equal to delta G standard of the reaction, plus, what if I factor out an RT? RT ln of products minus ln of reactants. We're almost home free. Products minus reactants as ln's, An LN rule that you may not remember, a natural log rule, is if you subtract logarithms, it's like doing a division of the same logarithm. So if I'm going from my blue formula down here to the next slide, just because I've ran out of real estate, delta G reaction is equal to delta G non-standard is equal to delta G reaction standard plus RT ln of products over reactants. Have we ever seen products over reactants? Ooh, we have. If it's not at equilibrium, which these reactions often are not, we've called that Q. We went through a lot of writing here, and maybe you followed along, maybe you didn't, but what's my take-home message, executive summary? The difference between delta G standard and non-standard, things we can find in tables, things that we really need to know to help determine if a reaction is, not help determine, to determine if a reaction is spontaneous or not. How do you find delta G non-standard if all you can look up is delta G standard? We found delta G non-standard is equal to delta G standard plus RT ln of Q, where Q is products raised to their coefficients divided by reactants raised to their coefficients. Yeah. If you didn't follow along my derivation, that's okay, but this is the take-home message of why we did all of that to come up with this new formula. Q, remember, is how far the reaction has proceeded. It's any time other than at equilibrium. If Q is any time other than at equilibrium, what if we talk about, well, what if we talk about this reaction at equilibrium? At equilibrium, delta G non-standard is equal to 0. So that's delta G standard of the reaction plus RT ln of at equilibrium, we call it K instead of Q. So I can pull this to the other side of my equation, and the reason I'm going to write it this way is because it's how you'll see it more often. Delta G reaction equals negative RT ln of K. So that long equation that was delta G non-standard is equal to delta G standard plus RT ln of Q that we sort of walked through the whole derivation of, we use that equation at equilibrium to come up with this one, and this equation we will see very frequently in our thermodynamics section. We're not far from finishing our thermodynamics section. This is the last video, actually, but we'll see this relationship between G and K a lot. Okay, how do we solve for things using this equation? The delta G standard is equal to this. So what's the value of the equilibrium constant? Well, delta G standard is equal to negative RT ln of K, and I'm going to say that it's Kp because that's what they've asked for specifically. That means negative 33.4 kilojoules equals negative 8.314 joules per mole Kelvin times 298 Kelvin ln of Kp. And you say, and I say, what did I do wrong? Oh no, what did I do wrong? Well, this is in joules and this is in kilojoules. You have to make the units match. It is a big deal that you make the units match. So I don't care if you change one to joules, if you change both to joules or both to kilojoules, but you got to make the match. I'm going to make it negative 33,400 joules instead of kilojoules and do my math that way. So that's negative 33,400 divided by negative 8.314 joules per mole Kelvin times 298 Kelvin. That equals ln of Kp. And if I did my math correctly, I've got ln of Kp equals 13.48. And it's probably been a minute since you did something with some ln's. But how do you make the ln go away? Ln is a natural log, and natural logs are base e. So you e to the, both sides, e to the 13.48 means Kp is equal to 7.156 times 10 to the 5th. That's a pretty large value. That's okay. Should it be a large value? Yes. My delta G is negative. That tells me my reaction is spontaneous, and spontaneous reactions must always have K values greater than 1. If you got a K value less than 1 and a negative delta G, you did something wrong in your math. It's a great idea to go back and check. Always, always, always. Okay, so one more equation. So many equations in this thermodynamic stuff. We have said that the value of K changes with temperature, but how do we calculate? Now we can calculate that change. We have two formulas for delta G. Negative RT ln of K, delta G standard. Negative RT ln of K, and H minus T delta S. Delta H minus T delta S. If we set those two equal to each other, negative RT ln of K is equal to delta H minus T delta S. We can solve for this ln of K term to help us determine how K changes with temperature. So the first thing I'm going to do is ln of K equals delta H minus T delta S over negative RT. Well, I can simplify that with negative delta H over RT minus negative delta S over R, and my T's cancel out. I don't know why I put it on the end, but minus negative would become plus the positive, so that's ln of K equals this. And I'm going to write it one more way. All I'm doing here is negative delta H over R times 1 over T plus delta S over R. This equation is called the Van't Hoff equation. You don't have to know the name of that, but sometimes I have called it by name. The reason that I wrote it in this bottom way is because if I plot the ln of K on the y-axis, ln of K on the y-axis over there, and 1 over T on the x-axis, 1 over T on the x-axis, I get a line that has a slope of negative H over R and a y-intercept of delta S over R. So if this line is my slope, it's a negatively sloped line, so that must mean that delta H itself is a positive number because there's a negative in my formula, right? So this must be the data for an endothermic reaction because it's got this negative slope. If it were an exothermic, it would actually have a positive slope. Negative times a negative would be a positive. So this is a negatively sloped line, and I could solve for different y values given different x values. I can do lots of things with this Van't Hoff equation to determine how K changes as temperature changes. This equation is a great way to write it. It's the slope-intercept form. Yeah, maybe you remember that. So that was the point slope form. ln of K equals negative delta H over R times 1 over T plus delta S over R. Brain fart. You might see it written in this way pretty frequently, but you may also see it written this way, which is the point slope form. So 2 y values, 2 K values, and 2 temperatures, find a delta H or something like that. If given a plot, we can find the slope of that plot to find delta H of our reaction. If given a plot, we can find the y-intercept of that plot to find delta S of our reaction. If given some 2 data points from a plot, we could find a delta H, and then we could actually go through and calculate a delta S using this kind of thing. One more way that you might see this takes advantage of an ln rule, where the ln of 2 things that are subtracted is like division. K1 over K2, these are equilibrium constants, big Ks, they look like small Ks kind of, but ln of K1 divided by ln of K2 is negative delta H over R, my H disappeared, 1 over T1 minus 1 over T2. There are a few different manipulations that you could do distributing that negative, for instance, so be careful with the formulas that you use because they can be written in lots of different ways and still be a correct formula. So the difference in these is just taking advantage of ln rules, This is this is slope-intercept form. This is point-slope form. This is another version of the point-slope form. Some of them have distributed this negative throughout the parentheses. Some of them do a little more math manipulation. They're all valid formulas of the Van't-Hoff equation, but the way things are represented are a little bit different throughout. So stick with one formula and use it and use it and use it. All right, that's the end of thermodynamics. Boy, that was quick, but that's the end.